Remember, we split our data into training and test data frames. 70% of the data went into the training data frame and 30% into the test data frame. Now we will use the test data frame to evaluate the predictive capabilities of the model. We will do this by calling the predict function and passing to the function the trained model and the test data frame. The function will use the trained model to predict delays from the test data frame and return an object containing the predictions. Now that we have the prediction, we can evaluate how well the model predicts flight delays. To make it easier to evaluate the model's performance, we use Caret's interestingly named confusion matrix function. We pass to the function the prediction object and the column we are predicting. The confusion matrix provides us with groups of performance statistics about the model's predictive capabilities. The first set of statistics is a matrix that compares the predictive and actual values for delays on the prediction and reference axes. Let's label these values with letters so we can use them in equations. A is the number of flights in the test data that were not delayed when the model predicted they would not be delayed. B is the number of flights in the test data that were delayed when the model predicted it would not be delayed. C is the number of flights in the test data that were not delayed when the model predicted it would be delayed. D is the number of flights in the test data that were delayed when the model predicted it would be delayed. Below the matrix is a set of statistics derived from A, B, C, and D. These statistics quantify the capabilities of the model in terms of standard measurements. Let's review a few key statistics about our model. Accuracy is the ratio of the model prediction to the correct answer. That is, predicting that a flight will be delayed when it is delayed, and predicting that a flight will not be delayed when it is not delayed. Mathematically, this is A plus D divided by the number of test rows. Our model seems pretty good on accuracy, achieving 0.7997, which is better than the target goal. But before we celebrate, let's take a look at some other statistics. Sensitivity is the measure of how the model predicts no delay when there is no delay. This is A divided by A plus C, and at 0.9970 is excellent. Specificity is the measure of the model's ability to predict delay when there is delay. Specificity is D divided by B plus D. Unfortunately, here the model is poor at 0.016. Notice this is mostly due to D, predicted delay arrivals at 31, being so much smaller than the actual number of delay arrivals, B plus D, 1938. We definitely need to increase the model's ability to predict arrival delays. A few more interesting statistics are the predictive values. The positive predictive value, which predicts when there will be no delay, is 0.801, which is pretty good. However, the negative predictive value, which predicts when there will be a delay, is 0.5741, not so good. So even though we hit our target for accuracy, we still have some work to do.